Hi everyone, thanks for coming to my recording. My name is Nigel Bosch, and today I'll be talking a bit about some research that we've done over the past couple of years to develop a method to enable analyzing discussion forum posts in online courses, and specifically addressing the privacy issues around that. So the reason we might want to analyze discussion forum posts is because there's a lot that can be learned via natural language processing in EDM types of analyses. So natural language processing has been used on discussion forum posts for things like measuring question asking and self-regulated learning, measuring MOOC completion rates, measuring cognitive presence of students in online courses, looking at engagement in online courses, and a variety of other things. So it's a very fruitful source of data, but there are some privacy issues as well, because students are not very cautious about privacy. They aren't apparently not really thinking that much about the information that they're putting online or about how it might be seen or used later. So, for example, this is a real forum post from a student who said, "Hi guys, my name is some name, but I prefer to be called some other name. I was born and grew up in somewhere, but I moved to somewhere else when I was in 7th grade." So this is a lot of personal information, things that we should not really have access to as researchers, or things that we can't even legally have access to sometimes as researchers. So we need some way to be able to identify those person names and place names and to remove them from the discussion forum posts before we can even access the data for research purposes. So there are a variety of privacy concerns that come up in natural language processing analyses, like students' names or addresses, hometowns, locations, which are really place names, as well as email addresses, phone numbers, URLs, and other things. In this research, we were mostly concerned with identifying names and place names. The things like emails, phone numbers, URLs, other things like student ID numbers, those are relatively easy to find and remove via regular expressions or just template matching. These names and addresses, those are the tricky parts to find. So there are some existing approaches that can kind of solve this problem that we initially started with. One of those is template matching with known names. So if you know the names of everyone in a course, you can find them and remove them relatively easily. But this is a problem if there are unknown names, especially if students provide nicknames or if you just don't have a course roster with everyone's name in it, as well as misspelled names. This does happen from time to time. And unexpected names. So for example, students talk about their place of work, which can be identifying information and should be removed. There are also more sophisticated approaches like named entity recognition that try to address some of these problems by figuring out what is a name from the context of the sentence in which it occurs. So these approaches are a bit more powerful. We had some successes with these, but we're still able to foil the approach relatively easily because of problems like new contexts. So if the model, the named entity recognition model, often a big deep neural network, gets applied in a new context with different types of data than it has seen, it will be less successful. Also, there can be problems with misspellings. It turns out to be relatively easy to foil the named entity recognition with certain misspellings, name misspellings, and non-narrative text. So a lot of the time students participate in forums that don't necessarily require narrative text. They may be posts of lists of things or even just a list of names as they sign up for a group project, for example. That's one issue we ran into. So we took a different approach that is focused on generating very few false negatives. We don't want to miss names if we can help it. And so this starts off by considering the conjecture that words that are not in the dictionary might be names. So what we do is we look at all non-dictionary words in forum posts, figure out which of those are names, and remove those from the posts. If it isn't in the dictionary, if it's not in the dictionary, we figure Well, that could be a misspelled word, or it could be a name, or it could be something else. So let's go through all of those and figure out which ones actually are names. Of course, there's a problem, which is that some names are in the dictionary. Names like Grace or Ryder or Max, and names of places like Reading or Coffee or Bohm. So what we do instead is we start with the dictionary and then remove the list of known names and locations from a very large database, leaving us with a dictionary of words that are not any known name. Then we can remove that dictionary of words from all of the words in the forum posts, leaving a list of possible names of locations or people. Some of these will certainly not actually be names, but that narrows it down quite a bit. So then what we did was manual annotation of these as name or not name, and then applied a machine learning approach to automate that annotation. And in fact, initially, we just did the manual annotation and called it good enough. We did that for a year or so before that got out of hand in terms of scale, and we really needed to automate that step as well. Then once we have that list of names, either through annotation or a machine learning approach, we remove those identifiers from the forum posts, which is relatively straightforward. So the manual annotation that we did for this project consisted of 2 raters going through 3 rounds of annotation to develop a shared annotation guide. And they achieved fairly high agreement, kappa of 0.842, on a development data set of 2,588 instances, where an instance is one possible name that may be a name or not a name. Then we also looked at 2 holdout data sets of 600 each. The first 600 coming from a later semester of the same course that was in that original development data set. The raters achieved fairly good agreement on that as well. And a second data set from a different course where only one rater completed the task given the previous high agreement of the 2 raters. So that separate course had a different learning management system, different forum software, and very different participation structure. So it served as a good test of the method's generalizability. So for the machine learning model, we extracted 2 different types of features, some that were densely distributed, which we called densely distributed because they have a wide range of values and very few zeros. So those are things like the count of occurrences, how often did the possible name occur, what proportion of the occurrences that were in the middle of a sentence were capitalized, what proportion of occurrences were at the beginning of the sentence, and a bunch of others that are in the paper, if you're curious. Then we also had sparsely distributed features, which were word presence features. So these are just 1 or 0 features, often 0, which were simply descriptions of which commonly occurring context words preceded that possible name. So words like hi, for example, is a great indicator that the next word might be a name. So we used 2 different machine learning models applied to these features. The first was extra trees, or extremely randomized trees. This is very similar to a random forest. It's invariant to the feature distributions, so we could lump all of those 2 types of features together despite them having very different distributions. And the second was a customized deep neural network where we tried to address this difference of feature distributions by having one set of inputs that were for the dense features, where we regularized them, those inputs, the activations, using L2 regularization, which is a little bit more suitable for that. And then the sparse features we regularized with L1 regularization. Since there were a larger number of those, we wanted to select only the most important ones, and L1 regularization is a good way to do that in a neural network. So then we merged those layers together and trained some more deep layers, and in the end we end up with a prediction just like extra trees of the probability of name or not name. And there's more detail on that in the paper if you're curious. So to train these models, we used 4-fold cross-validation in the development data set. And within each training fold, we used nested 4-fold cross-validation for hyperparameter tuning. For extra trees, we tuned the depth of the trees and the proportion of features that are randomly selected for each tree. And for the custom neural network, we adjusted the number and the size of the layers, the strength of the regularization, and a bunch of other factors. Again, that's in the paper if you're super curious. And then the final holdout model, that's the one that we actually want to use in practice going forward, is just trained again once at the end on the entire development data set, and that's used to make predictions on the two holdout data sets. So the results on the cross-validated on the development data show that the extra trees model was quite accurate. The AUC 0.971 is versus resolved human annotations. So what that means is the two manual annotators discussed any differences that they had in annotation and came to an agreement about what the correct categorization was. And that's the same for kappa, same set of labels. For the custom neural network, the AUC was a little higher, kappa was a little bit higher as well. And then we also did a fusion where we averaged together the two predictions, which produces a similar AUC and a kappa that's about between the two. And one thing that we note in the paper is that this fusion is a little bit more conservative about predicting not names, so it over predicts the names a bit more, which is a desirable thing in this case because we want to really avoid false negatives. So for the holdout results, the first holdout data set is the later semester of the same course. The extra trees model has, again, a high AUC, not quite as high of a kappa, 0.77, but that's only a little lower than the human annotator's initial agreement. And the custom neural network had very similar kappa and similar AUC. The fusion outperforms either of those two individual models by a small proportion, but again, it's a more conservative model, so we prefer this one. The holdout results on a new course, again, had fairly similar accuracy. For both the extra trees model and the custom neural network, slightly lower kappa for the custom neural network, but the fusion slightly outperforms either of those individual models. So in conclusion, it works pretty well. It isn't perfect, but the most important thing is that it's very conservative about its guesses. So it gets almost all, perhaps even all in some cases, of the name words. So that's what we really want to capture. In the paper, we go into this in more detail, but essentially analysis of errors that the model makes shows that the predicted errors, or the errors in the predictions, tend to align with cases where the human coders were also uncertain in the development data. So cases where the humans disagreed were also cases where it was more ambiguous for the model. In practice, the fusion model makes very few false negative errors, which is good. Those are the missed names, the things we really want to avoid. It makes a few false positive errors, definitely, but it's fairly straightforward for humans to enter the loop between this name, not name prediction step and the step where we actually remove the names from forum posts. So in practice, what we do is apply the model to predict what names are and aren't names, or what words are and aren't names, and then it outputs a list ranked by how common they are, so that a human can just look at the top few most common names and decide, yes, these actually are or are not names, and can remove them to avoid those false positives that might have a big impact on words being unnecessarily removed. So we're actually using this, always nice, with a project to be able to use it. It's proven to be quite useful for allowing us to access data to do natural language processing and even manual annotation of discussion forum posts for other things. So we've looked at things like help seeking, question asking, metacognition, and others in tens of thousands of discussion forum posts, which is only possible if they are anonymized. So thanks very much for watching this recording. I'd be happy to take any questions that you have in the live session, or you can always email me. And if you're curious to look at the software, I put a link up here. it is still occasionally updated when we think of new ways to potentially improve the accuracy. And also thanks to IES for supporting this research.